Okay.
So, can you see my title slide?
Yes.
Yep.
Okay. So, hello everyone. I'm pleased to share with you today what was the focus of my PhD research during the last 5 years at the University of Chile, under the supervision of Martin Reich and Fernando Barra, with a very close collaboration with Adam Simons' research group at the University of Michigan. So I'm going to focus my talk on El Laco, which is an enigmatic deposit discovered in the late 50s in the high Andes of northern Chile, which represents the youngest and one of the best preserved iron oxide mineralization examples on Earth. And it's therefore considered as a key location to study the processes that form iron oxide apatite IO8 systems, and has been the focus of decades of research, giving rise to much of the genetic models that have been proposed to explain the genesis of IO8 systems. So the Laco volcanic complex, shown here in a blue triangle, is located in the Chilean Altiplano, and it is part of a northwest trending volcanic chain in the Miocene Pleistocene volcanic arc in the Andes. This volcanic complex is mostly andesitic in composition. Its volcanic history includes explosive volcanic eruptions, a stage of stratovolcano collapse, and late resurgent activity. Now, looking at the geology of the Laco volcanic complex itself, I just want to point out the occurrence of at least 6 R bodies, shown here in black and here in reddish black, and that outcrop on the flanks of this collapsed stratovolcano. And as we can see here, they extend below to the surface, forming large breccia bodies. The outcropping part of these ore bodies are composed by around 90% of model magnetite, with some minor pyroxene and very scarce apatite. And they have been interpreted by several authors as magnetite lava flows. And now in the next slides, I will show you why. Here we can see some photographs of the ore bodies that outcrop at the surface, which have textures and surface structures that bear a striking resemblance to basaltic lava flows. But let's remember they are formed almost exclusively by the mineral magnetite. These volcanic like textures, are present in all of their bodies and include lava flow and vesicular textures, like this one, for example, vertical degazing conduits, like this one, which can only be compared with basaltic volcanic products, either from Hawaii or from Iceland, for example. So now, let's see what are the hypotheses that have been proposed to explain the origin of this very enigmatic deposit. Basically, there are 2 classical and fundamentally different genetic models. The first one is liquid immiscibility. This hypothesis invokes the unmixing of a parental silicate malt into iron phosphorus-rich malt and a conjugate silica-rich malt. In the Laco magma chamber, after separation during cooling and decompression, the silica-rich malt remains at depth, while the iron-rich malt can ascend up to the surface and flow, crystallizing as massive magnetite ore bodies. The second one is metasomatic replacement. This view proposes that iron-rich hydrothermal fluids completely replace pre-existing andesitic lava flows through metasomatic processes, including all their silicate minerals and all the ground mass of these andesitic rocks, and replaced by the mineral magnetite and preserve all the original volcanic textures, yes. So one of the things that has hindered to establish a consensual model for Laco is that all the previous genetic models have been built based on field observations for one side and geochemical data of magnetite from the ore bodies that outcrop at the surface. So when we started to study El Laco, we observed that all the information previously published was based on studies that collect samples only at the surface. So we noticed that we're just looking at the tip of probably a large iceberg that represents a complex mineral system at depth, which is key to understand the formation and evolution of this deposit. So here is where our motivation comes up, and what we did was to collect drill core samples, as I show you here in blue symbols, which intersect the ore bodies at different depths and can therefore offer a better picture of the entire mineral system. We combine this unique sample set with samples of volcanic rocks collected from the main volcanic units that host the iron mineralization at the lab. So here we have our approach. This study was based on three main components: mineralogy, microtextual observations, and geochemistry, with a main focus on the mineral magnetite and also on the second most abundant mineral phase in the ore bodies, which is cranopyroxene. So we investigate the microtexture and chemical composition of magnetite and clinopyroxene grains from the ore bodies, from the bottom to the top of the system, and we couple this information with magnetite and clinopyroxene data from the andesite post-rock. Here are the analytical techniques. We combine SEM observations, high-resolution elemental mapping using microprobe and synchrotron XRF microscopy, with major, minor, and trace element geochemistry using an electron microprobe and a laser ablation ICDMS. So in the next slide, I will first present our results for magnetite, and then I will move on to the clinopyroxene data. So let's start looking at the magnetite in the Laco volcanic rocks. We observe that the majority of the magnetite in these andesitic rocks occurs forming glomerocrest, as I show here in white circles, forming glomerocrest with clinopyroxene, orthopyroxene, and apatite. This is a synchrotron three-elemental map that show magnetite in pink, orthopyroxene in blue, and clinopyroxene in light green. So in terms of textures, magnetite in this glomerocrest shows ilmenite exsolution lamellae, exhibiting both trellis and sandwich type textures. Here we have a schematic illustration showing a representative drill core from a lagar bodies. I'm going to use it to show you significant mineralogical, textural, and geochemical variations in magnetite from depth to surface. So on the basis of these variations and going up from the base of the system to the top of the system, we can divide the Laco bodies in three main zones. A deep zone of the magnetite-rich breccias, characterized by magnetite grains showing ilmenite exsolution lamellae and inclusion-rich cores surrounded by pristine veins. These textures are consistent with magnetite from igneous or high-temperature magmatic hydrothermal environments. Then we have an intermediate zone of the breccia bodies dominated by magnetite grains showing clearly hydrothermal textures, such as dissolution reprecipitation textures and oscillatory banding. Finally, we have a shallow and surface zone dominated by massive magnetite that form aggregates in case forming mosaic textures, and that exhibit moderate to pervasive alteration degrees with hematite and goethite formation. Magnetite in these upper levels is texturally consistent with magnetite, with hydrothermal magnetite affected by submerging processes. And here I want to highlight that the titanium concentration in magnetite systematically increases from the surface to depth. So we have multiple generations of magnetites in Laco bodies as a function of depth, which are probably recording different ore forming conditions. So now let me show you briefly some of the textures that are key to understand the story of the Laco. Here we are looking at the magnetite from the deep zone of the breccia bodies. This is a titanium XRF map of a large magnetite grain in which we can see exsolution lamellae and ilmenite grains occurring in the core of this magnetite grain. These ilmenite grains in turn show simplectite-like textures, which are typically described in mafic layered intrusions. So this is something to keep in mind. The other important textures that I want to show you is the one that dominates in the intermediate levels. Magnetite from this zone show abundant re-equilibrium textures, evidenced by highly resorbed cores surrounded by oscillatory and sector zone rims. These textures have also been observed in several other AOA and iron skarn systems, and described as formed by multiple pulses of hydrothermal fluids under dynamic physicochemical conditions. Now I'm going to show you some geochemical data for magnetite. This is an aluminum plus manganesium versus titanium plus vanadium plot proposed by Patrick Noble in 2014 to discriminate magnetite from different mineral deposits formed at different conditions, ranging from magnetite formed at purely magmatic conditions at the top right, and to magnetite precipitate at purely hydrothermal conditions here at the bottom left. So here we use this diagram to explore the geochemical affinities of magnetite in terms of its crystallization conditions. So first we have magnetite from the host and the site in blue that consistently plots in the igneous field. Then we have magnetite from drill core samples from depth in green, plotting mostly in the higher temperature magmatic hydrothermal fields, like porphyry, for example. And finally, we have here in yellow magnetite from the ore bodies that outcrop at the surface in orange, plotting towards the lower temperature hydrothermal fields. So basically, what we're observing here is that igneous magnetite in the host andesite is trace element rich, while magnetite in the ore bodies show a progressive trend of depletion in minor and trace element from the deeper portion of the deposit to the surface. And that is consistent with a cooling trend from hot magnetite at depth to progressively cooler magnetite in the shallower levels of the Laco. Here we have some other trace element plots and discriminant diagrams, vanadium titanium ratio versus iron content here on the left. And again, what we can see is that magnetite in the host andesite shows an igneous affinity, whereas all the data for magnetite from the ore bodies indicate a hydrothermal affinity. And here on the right side, I have vanadium versus gallium plot, showing that magnetite in the host andesite is the most trace element rich. And as we move from deep zone towards the surface, the vanadium and gallium concentration in magnetite decreases progressively. We interpret these variations as a transition from purely igneous conditions to an evolving system, increasingly influenced by hydrothermal circulations, with ore fluids that chemically evolve towards more depleted composition during progressive cooling. Now, let's see what clinopyroxene can tell us about the processes operating in this volcanic ore system. Here on the left side, we have an XRF map of a clinopyroxene from the glomerocrest from the magnetite-rich glomerocrest. This grain show a reserve core and alternating chromium and titanium-rich layers. These textures in volcanic rocks have been interpreted as evidence of mafic magma recharge into a more differentiated magma reservoir. And on the other side, clinopyroxene from the ore bodies, like magnetite, we observe multiple generations of cyanopyroxene, including highly resorbed cores and rims displaying oscillatory zoning, and these textures, which also reflect multiple pulses of hydrothermal fluids under very fluctuating physicochemical conditions. Now, if we look at the chemical composition of this cyanopyroxene from Laco, I'm not going to go into details about this. I just want to highlight that cyanopyroxene grains from the host andesite and from the R bodies are chemically different, as we can see here in these plots. And now, if we compare their chemistry with chemical data of cyanopyroxene from two magmatic and hydrothermal end members, we observe that a very nice correlation between the composition of cyanopyroxene from the host andesite with the composition of cyanopyroxene from mafic layered intrusions, shown here in gray fields in the background. And on the other hand, the composition of cyanopyroxene from the R bodies, here in green, blue, we can see that it behaves very similar to the composition of hydrothermal cyanopyroxene from iron skarn deposits, shown here in light blue fields. Therefore, these trends are further confirming a magmatic affinity for cyanopyroxene from the andesite, as expected, and an hydrothermal chemical signature for the cyanopyroxene from the R bodies. Finally, we put all this data together and developed a new genetic model that consistently explains most of the features observed at the Laco, which we think cannot be fully explained by either of the two previous hypotheses that I showed before. This model explains the formation of the magnetite R bodies as the product of a combination of magmatic and hydrothermal processes operating during the evolution of this volcanic system. This model involves sequential steps that include magnetite crystallization, igneous magnetite crystallization, mafic magma recharge that trigger volatile saturation and the exsolution of a magmatic volatile phase. Then in a later stage, interactions between these processes led to the formation of an ascending iron-rich magmatic hydrothermal fluid that is later injected into the upper levels of this volcanic system through collapse-related structures, forming large breccia bodies at depth and massive bodies at the surface. And as I showed before, these are bodies, these are fluids chemically involved during their ascent towards more depleted composition, precipitating magnetite with an increasingly hydrothermal geochemical affinity in response to cooling and decompression processes. Finally, to conclude, I would like to highlight that this model is built on probably the largest and most comprehensive data set ever produced for Laco. However, this is just a model that is open to changes and further improvements. And in order to continue refining this model, here I provide some potential next steps in terms of future research that could contribute to our understanding of this deposit. And they include, for example, magnetite thermometry by using the magnesium in magnetite thermometer recently proposed by Canida and Lacours in 2020. And alternatively, it would be very interesting to carry out a geochemical study of fluid inclusions host in ore-related cyanopyroxene and apatite, and in order to reveal the chemical and physical evolution of the ore fluids at the Laco from the roots of the system to the surface. Thank you for your attention.
That was great, Tomas.
Sorry.
So does anybody have any quick questions for Jose Tomas now? Do you want to ask a question now or do we want to wait?